In this video, we're going to look in more detail about how dynamic chemical equilibrium forms and look at how we can represent equilibrium systems graphically. If we consider this hypothetical equilibrium system where A represents all of our reactants and B represents all of our products, let's look at how an equilibrium system forms by starting with 100% of our mass being in the A form here with nothing in the B form. Now, if we consider which reaction rate is greater, forward or reverse, the answer is pretty obvious that the forward reaction rate is greater, because if we have no products, that means that the reverse reaction is impossible, which means that our equilibrium arrow would have to be written like this to show that there is no reverse reaction taking place. As a consequence of this, some of our A is going to be converted into B, and therefore the concentration of our reactants A is going to decrease over time as we produce B, and therefore the concentration of our products B are going to increase over time. Now we can represent this graphically like this. If the diamond-shaped squares represent the concentration of A, we can see as our reaction progresses that the concentration of A decreases while the concentration of B increases, and as we reach approximately 6 seconds on the graph, we see that the concentrations of A and B begin to stabilize right here. And when these concentrations have stabilized, remember that the point at which the concentrations of our reactants and products become constant, this is one of the conditions that is required for dynamic equilibrium to take place. So we see it very obviously occurring on this graph here, and the reasons why an equilibrium forms have to do with rate. Now, if we consider that concentration is one of the factors that affects reaction rate, as the concentration of our reactants A decrease, then our forward reaction rate is also going to decrease over time, because if we have less of A, there are going to be fewer collisions that take place, and therefore fewer chemical reactions, and therefore the rate of our forward reaction is going to decrease over time. The opposite is true of B, because as our concentration of B increases as we make more products, that means that there are going to be more collisions or chemical reactions, which means that over time, the rate of our reverse reaction is going to increase. Now, at this point where the concentrations of A and B remain constant, that is the point at which our forward and reverse reactions become equal. Now, we can use this graph here to actually calculate the value of KEQ, our equilibrium constant, which we know is the concentration of all of our products divided by the concentration of all of our reactants, which are simply the concentration of B divided by the concentration of A, which, if we see on the graph here, the concentration of B at the equilibrium point is 1 mole per liter, and the concentration of A at our equilibrium point is 0.2 moles per liter, which comes out to being 5. Now, we can represent the change in rates on a separate graph here, and as we've already established, as the concentration of A decreases, that means that our reaction rate for the forward reaction is going to decrease as well, which coincides with an increase in the reverse reaction rate. So as our reaction approaches equilibrium, which again takes place at approximately the 6-second mark, that means that our rate forward is going to become equal to our rate reverse. And therefore, we can conclude here that this is the point where the concentration of the products, B, divided by the concentration of our reactants, A, begins to become constant because if the two rates are the same, that means that the rate of producing reactants and producing products becomes equal, and therefore no concentration change occurs. So we see by representing equilibrium systems graphically in terms of both concentration and in terms of rates, it becomes very easy to predict when an equilibrium situation occurs. In conclusion, we can do a summary of all of the conditions that are required for and observations that we see at dynamic equilibrium. The principal cause is when the rate of the forward reaction becomes equal to the rate of our reverse reaction, which means that the rate of formation of products by the forward reaction is equal to the rate of consumption of the products in order to form the reverse reaction, and the opposite is true for reactants as well. Now remember that if the concentration of products and reactants does not change, we are not going to see any observational changes, meaning that no macroscopic changes occur in the reaction, but this does not mean that nothing is happening within the reaction. And because of the fact that our reactant and product concentrations remain constant, if we take the concentration of all products and divide by the concentration of all reactants, which are both constant at this time, we get a constant number which we can use for calculations, which is what we call KEQ. And remember that this can only occur in a closed system, because if any of the products or reactants escape from the reaction, the reverse reaction is no longer possible.